Welcome back. In the previous session, we tried to understand some of the basic concepts of Spark, and we are going to cover some more new concepts in the session. But first, let's try to do a quick recap about what we discussed last week. So Apache Spark is a unified analytics and computing engine used for parallel processing of big data in large computer clusters, which is nothing but Spark provides a framework and an engine where we can write a higher level abstract code using programming languages like Java, Scala, Python, R, and SQL. And Spark automatically does the work of data distribution and data processing across huge computers. And we need not worry about the underlying infrastructure and cluster management, and Spark takes care of all those. We just need to focus on what we are trying to achieve, which is nothing but data transformations and applying business logic on the data. And we try to understand the core difference between Apache Spark versus traditional MapReduce. Apache Spark is much faster because of the in-memory processing capability that it has, whereas traditional MapReduce usually does the data switching from primary memory to the secondary memory, due to which the data transactions or data processing gets delayed. And as we know, Spark is very much easier to learn, easier to implement, and highly scalable with many features like batch data processing, real-time data processing, graph data processing, and all those stuff, whereas MapReduce does not provide all those. And there are multiple individual technologies like Hive or Apache Scoop or many other individual technologies to support certain features. If you want to do a machine learning on a traditional Hadoop tech stack, you'll have to go to an individual service that provides that functionality. Whereas in Spark, it comes by default with a certain set of features, including batch data processing, stream data processing, machine learning, as well as graph data processing. And as we can recall, the core difference can be easily described by this image where in traditional MapReduce, we do the data movement from primary memory to secondary storage continuously during multiple maps and reduce phases. Whereas in Spark, everything will be brought together at once into the memory and processed and finally loaded into the external storage, which is nothing but the lazy evaluation concept. And then we also try to understand the various language APIs available for us in Apache Spark. As part of this course, we will only use Python and SQL to write PySpark applications and Spark SQL applications in Spark. And RDDs are the fundamental data structures of Apache Spark. So an RDD is an immutable distributed collection of elements of your data partitioned across various nodes in our cluster that can be operated in parallel with a low-level API that offers various set of functionalities which are categorized into transformations and actions. These are nothing but an RDD is like the fundamental data structure of the Spark. To understand easily, if we take a programming language like Python, Python has data structures like lists, tuples, dictionaries, and each and every one of those data structures have certain built-in functionalities. Let's say if we take a list, we can actually append elements to the end of a list. Or if you want to slice a certain set of items of the list, we can do slicing. Or if you want to get a particular element based on the index of a particular value in the list, then we can use indexing. So similarly, dictionaries have certain set of functionalities. If you want to add items to a dictionary, then we have certain set of functionalities. So similar to those functionalities, RDDs are nothing but the fundamental data structures like lists and tuples, but these are related to Spark. And similar to lists having various functions, built-in functions, RDDs also support certain set of built-in functions which we can make use of to do the higher level operations. Moving on. These are the basic attributes of an RDD, which are nothing but the properties of a resilient distributed data set. And this shortly describes about ways to create an RDD, where we have data data variable, which is a list variable, and it has various items in it. Now, if you want to convert this list variable data into an RDD, then we use SparkContext.parallelize method, and we'll pass the data variable to that parallelize method in order to convert that list into an RDD. Now, when an RDD is created, by default, Spark automatically distributes or partitions the data into small blocks. And when the Spark application is completely written and submitted to the Spark cluster automatically distributes the data, and one particular block of data will be provided to one particular piece of the cluster, like one particular piece of the executor node. And similarly, if we have 10 partitions created, then each one of those will be provided to one executor node, and the further processing happens automatically. So let's try to understand what are transformations and actions once again, because this is where we stopped last time. A transformation is a function that provides a new RDD from an existing RDD. But when we want the actual data set, at that point, an action is performed, which means, let's say if we have data in a SQL table, which has 10 columns, and if you want to filter the records based on a particular filter logic, let's say if you consider a student table that contains student ID, student name, section name, and student score. And if you want to filter the records of students whose scores are greater than 50%, then you'll write a SQL query in general. But if you want to do the same using an RDD function like in Spark, then you will have to write a Spark code where you will have to make use of some built-in functions. And those inbuilt functions are categorized into transformations and actions. The functions that help us to write the transformation logic or the selection logic and the filter logic are considered into transformations. And an action is nothing but a function that actually initiates or invokes the execution or the actual execution of the entire transformation logic till that point. We'll try to understand more about it in the coming sessions, where we'll try to write some piece of Spark code, and you'll easily understand the main difference between a transformation function and an action function. So transformations are classified broadly into two types: narrow transformations and wider transformations. Why do we have two different categories? What do we mean by that? Narrow transformations, in narrow transformation, all the elements that are required to compute the records in single partition live in single partition of the parent RDD. A limited subset of partition is used to calculate the result. Narrow transformations are result of a map and a filter. For example, let's take this image. Let's consider we have 10 records in our table, or we have 10 items in a Python list. Now, if we have submitted this particular piece of code to a Spark cluster, then automatically, based on the availability of cluster resources, it automatically distributes the data or divides the huge amount of data into smaller chunks, as you can see here. And each one of these small pieces is nothing but an RDD. Now, every one of these partitions will be applied with the same set of logic that is written. So you will write a higher level code, and you will send this data to each and every executor. And each and every executor takes the data as well as the code that you write, and the code will be executed on this data, on this data, similarly across all the partitions. Now, sometimes there might be a scenario where you would like to shuffle the data. So when Spark creates partitions, each and every partition goes to one executor node, right? Now, sometimes, let's say if you have written a certain logic where you would like to sort the data, consider the items in this list are unsorted, which means 12 might be here, 2 might be here, like it is unordered. Now you want to order it in a sequence of 1, 2, 3, 4, 5, 6, so on and so forth. If that is the case, and if data is not properly ordered, you might want to shuffle the data, right? Then the data will have to be moved from one executor to another, which causes data shuffles. So what we are trying to talk here is that a narrow transformation will always result in a single partition, which means if we apply a certain function, and after the execution of that function, if the result does not involve any data shuffles, and if it results only one particular result from the previous parent partition, then it is called as a narrow transformation, which means whatever the function that we apply here is actually causing no data shuffles and only causing one output from its previous layer of parent input, right? So if you see here, this is an example of narrow transformation. Let's say if I write a select query to sort these results, this will not affect anything because everything is already ordered and properly distributed. If you take any one partition, the order of numbers is properly done. Let's say if the numbers are in this order 3, 1, 2, then the numbers are unordered but within the same partition. Now these will be properly ordered within the same partition. But let's say if 1, 2, 4 are here and 3, 5, 6 are here, then there is a scenario to move the data value 3 from here to here and value 4 from here to here, right? So that is not the case here. So this is a narrow transformation, and the example that we just discussed is the example of wide transformation where it requires data shuffles. And when we do a data shuffle, we might end up in a single partition or multiple partitions. So that's all about narrow transformation and wide transformations. These come into picture when we are talking about optimization because if the data is small enough, and if the data is being moved across various computers, various executor nodes, which are nothing but computers, then it is good enough to do the operation. We need not bother about that. But let's say if you have two huge amounts of data, like let's say 10 gigabytes of data here, 10 GB of data, 10 GB of data like this. And if you're trying to shuffle the data here, we are basically wasting a lot of time in just moving the data across executors. Right. So it is just waste of time. But sometimes we cannot avoid these particular scenarios of data shuffling. But majority of time we'll try to understand what is happening and we'll try to optimize based on a given scenario. We'll have to do a trade-off. Moving on, Spark basic architecture. So let's try to go through a simple image which briefly describes about various aspects of a Spark cluster. Now, when you submit a Spark application, what happens is that there is always a driver process and there are multiple executor processes, which means what you can simply understand is that there is one parent computer, which is like the brain of the entire body. And there are individual computers, which are like individual body parts, arms, heart, lungs, kidneys, similarly, something like that. So until and unless the brain is working, individual parts of the human body doesn't work. Similarly, if the driver process goes down, so none of the process get executed, or there will not be any progress that we can observe about what's happening in the executors. So end of the day, driver process and executor processes are nothing but individual computers, but driver process does not do the actual computation. It is like the brain, which has information about every individual body part or every individual other computer that is actually doing the work. So executors are the places where the actual data computation, data transformations, actions, all of those are executed, right? So when you write a Spark code, when you submit it, what happens is the user code will be submitted to the driver node. And driver node understands, it will try to communicate with the cluster manager and it will get the information about what are the executor resources which are free and which are ready to compute. Let's say if there is a cluster that is utilized by multiple people, we will have to understand which executors are free. So that particular information will be holded by cluster manager, and cluster manager communicates the same to the driver process. And based on the availability of executors, the driver process allocates the code and the data to executors, and individual execution happens in the executors. And once all the execution is done, we can always track the execution of our jobs by contacting the driver. So if we go through the theoretical aspect, a cluster or group of computers pulls the resources of many machines together, giving us the ability to use all the cumulative resources as if they were a single computer. Now, a group of machines alone is not powerful. You need a framework to coordinate work across them. Spark just does that. Managing and coordinating the execution of tasks on data across a cluster of computers, which is what we just discussed. So there are a group of computers which are sitting idle. Now we need certain framework which has to communicate, or which has to provide an intermediate layer that does the communication, data management, data movement, execution of all the stuff that we want to do. So Spark just does that. Nothing but coordinating the execution of tasks and whatever, like whatever the functionality that we want to perform is being managed by Spark. The cluster of machines that Spark will use to execute tasks is managed by a cluster manager. And there are multiple cluster managers like Yarn and Mesos and standalone cluster manager and multiple others. We can even use Kubernetes or Docker to actually manage the resources like scale up or scale down, whatever. So, but the famous cluster managers in traditional Hadoop world and big data world are Yarn and Mesos, and Spark comes by default with a standalone cluster if you are running your Spark in your local computer. Now, when we then submit Spark applications to these cluster managers, which will grant resources to our application so that we can complete our work. That's pretty much what we are trying to do. Write the code, send the data to the driver node, which is further sending the data and the code to the executors by getting the information of availability of individual executors from the cluster manager. And further processing is happening down in the executors. Now, if you want to understand the core functionalities or works of a driver and executor, here are the points. Spark application consists of a driver process and a set of executor processes. The driver process runs your main function, sits on a node in the cluster, and is responsible for three main important things. Maintaining information about the Spark application, which is nothing but if you submit a code and send the data of a particular Spark application, then we need to understand whether a Spark job is running, or if it is in queued state, or if it has failed, or whatever the reason it might be. If you want to know the status, the driver node has to have the information about the status of the Spark application. So it does maintain that information, responding to a user's program or input, which means, let's say, if the program is expecting some input from the user, then driver mediates that communication between executors and the end user. And also, if you want to terminate a Spark application or Spark job, then there might be some stop button which we would like to click. So that process even is mediated by the driver node. And finally, analyzing, distributing, and scheduling work across the executors, which means based on the availability of cluster resources, like amount of RAM that is available, number of executors available, and number of cores that are available in each and every executor. So based on all these information that driver gets, the driver is going to allocate our data and code to those particular executor nodes where there are resources that are available. So Spark driver node does all these three important things. Driver process is absolutely essential because, as we said, it's like the brain of the entire Spark. It's the heart. Okay, they mentioned it as it's the heart of Spark application and maintains all relevant information. But I use my own example to explain it. It's the heart of a Spark application and maintains all relevant information during the lifetime of the application. Now, the executor. So unlike a driver, executor does not hold too much information about all the executors, but instead it has two main aspects to do. One is executing the code assigned to it by the driver, and the second thing is reporting the state of computation on that executor back to the driver node. If at any point in time the executor node goes down due to some temporary issue or out of memory issues or any error in the code, then that status has to be communicated to the driver, so the driver can send it back to the user, where the user can see the error message on the console. So it executes the code provided by the driver, as well as it communicates the status of the Spark application back to driver node. Now, coming to the first coding part of the entire Spark. So there is something called as SparkSession. Before we get into this particular concept, I'll try to refer to a simple example. If we are trying to go to a movie, or if you're trying to go to an exhibition, the first thing that we usually do is book a ticket or buy a ticket. So without a ticket, we will not be allowed into the theater or exhibition or any museum or any place, right? So if we have a ticket, we are allowed to watch a particular movie, or if you consider the example of an exhibition, if you have a ticket, you can go and visit any place in the exhibition or a particular zoological park. Similarly, in Spark, if you want to make use of the functionalities of Spark and execute your code with the functionalities of Spark, you need to get something like a ticket. In this case, we call it as a Spark session. So I'm trying to provide a realistic example so that we can relate better. So Spark session is more like a ticket. So if we have a Spark session readily available for us, then we can actually submit our code and execute our code across multiple executors. So in order to get that Spark session, we need to write a small piece of code that gets that token for us, that ticket for us. Now we can control our Spark application through the driver process called the Spark session. The Spark session instance is the way Spark executes, sorry, user-defined manipulations across the cluster. There is a one-to-one correspondence between a Spark session and a Spark application, meaning each and every Spark code that you submit will always have one Spark association with it. Without the creation of a Spark session, you cannot execute your code that you have written inside a Spark cluster. Okay, so the basic syntax goes like this. So there is this library and a module within which there is this Spark session function which we can use to create the Spark session for us. So Spark is the keyword. So instead of Spark, we can use any name, Raghu, Mark, Zuckerberg, Tim, or whatever the name it might be. You can give any name. It's more like a variable. Okay. You can give a variable and you need to assign that variable with the Spark session information. Now, the syntax for creating a Spark session is Spark session.builder. Builder is the method that provides us the functionality of creating the Spark session, and then master. As we were going through the slides, you might have seen a place in the previous slide, you might have seen different types of cluster managers where we have standalone cluster as well. So if you're running your Spark in your local computer, then you might want to specify the total number of resources that you would like to use based on your computer configuration, right? So basically, we are trying to provide information about the total number of cores that you would like to utilize and in which mode you would like to run. So this master function takes an argument about local off star, meaning local means run in the local mode, which is like your personal computer, like standalone mode, with and star meaning a wildcard. Let's say if you have 4 cores available in your computer, which are free to use, then based on the availability of those cores, Spark will automatically take those cores and run your Spark application within those 4 cores of your computer. And you can add some more configuration. This is just a basic simple syntax. You can give a unique name to your Spark application. Let's say if I am running my Spark application and if I would like to uniquely identify my Spark application, I can give an application name. So I can give Pujit or XYZ or whatever. So and also I can actually configure the amount of memory that I would like to allocate for my process. And the get or create is nothing but, let's say if there is an existing Spark session that is already created, we can actually make use of that. But if we do not have an existing Spark session, then the get or create will create a new one if we do not have an existing Spark session variable. Moving on. We'll try to come back to data frames in the next session. We'll try to Spark session code, like creation of Spark session variable, and we'll move further in the coming session. Now, so Spark session. Uh, as we have already started understanding Spark session, so Spark session is more like the entry point of Spark. It's more like a ticket or a token in order to access the functionality of Spark. But before Spark session, there used to be something called as a Spark context. So Spark context is the primary point of entry for accessing Spark capabilities, like the transformation functions and action functions. A Spark context represents a Spark's cluster connection that is used in creating resilient distributed datasets, accumulators, and broadcast variables on the cluster, which are various other concepts within Spark. A Spark context is also used to access Spark services, submit and perform jobs. Even you can actually submit your Spark application code through a command line as well. So even if you want to do that, you need to have Spark context created first as the first part of your Spark application. Now, this also allows access to two other contexts, which are SQL context and Hive context, through Spark context. Meaning, if any one of you who are seeing have background about a little bit of big data technologies like Apache Hive, then we usually have Hive metastore, and we can write SQL-like queries in Apache Hive. And if you want to, if you are working with the databases, I think majority of us who are going through this course will obviously have some knowledge about SQL. So if we might be pretty much familiar with SQL. So the beauty of Spark is that we can actually write SQL queries to transform the data. So we need not learn a completely new programming language to write a Spark application. So in order to write a SQL query and execute it as a Spark application, we need to have some sort of interface or medium that provides us that features, right? The features of Spark for our SQL queries. So for those reasons, there were SQL context and Hive context, which provides us the feature of writing and executing SQL and Hive-like queries using within Spark. So, and the Spark context provides those features as well. Now, the core difference between Spark context, SQL context, and Hive context are provided here. We need not worry about these three particular individual things for, right now because they are outdated. And we have a single Spark session which has the features of Spark context, SQL context, and Hive context. Previously, what used to happen is if we have a Spark context and if we want to write SQL queries, we need to explicitly create a SQL context. And let's say if we already have a Hive application, and if we want to use that Hive code and run in Spark, we explicitly need to create a Hive context. But with Spark 2.0 or from Spark 2.0, we got the new version of Spark Context, which unifies the features of Spark Context, SQL Context, and Hive Context. So we need not explicitly create every single one of them in order to use them. So from Spark 2.0, we got Spark Session, which encapsulates Spark Context, SQL Context, and Hive Context, offering a single point of entry for data frame and dataset APIs, as well as SQL queries, including those compatible with Hive. A Spark session in Apache Spark is the unified entry point for reading data, configuring the Spark application, and managing Spark jobs. It provides a way to interact with various functionalities such as Spark SQL, data frames, and dataset APIs. So we will come to data frames and dataset APIs in the coming session, but what you can understand is they are a way, an abstraction layer on top of RDDs to write an easy code or more understandable and manageable code for writing a Spark application. So data frames and both datasets provide a high level abstraction to write an efficient Spark application. Now, the basic syntax, as we saw earlier, for creating a Spark session is sparksession.builder.appName, where we can provide any name that you want for your Spark session. And you can give some configurations like spark.executor.memory, and you can give 2 gigabytes or 4 gigabytes or 10 gigabytes based on your computer resources. And if you do not have the resources, obviously, it's not going to allocate those resources for you. And finally, the get or create. And there are different configurations that you can give. The basic one is app name, as we have already seen, and then master, which we have seen in the previous presentation, where we usually set the Spark master URL to connect to, like whether you want to run it in a local mode in your local computer, or you might want to run your Spark application in a remote cluster of resources, like a local server that you installed at your home. And if you have configured a local host in that server, you can actually give that URL. And then if you want to give some more properties like executor memory, you can actually provide those as key value pairs. And then if you want to enable Hive support, you can give those and finally get out create. So a question to ask ourselves: why do we need to create a Spark session in Apache Spark? Can't we write and run Spark application code without it? As we continuously mention, without a ticket, we cannot get into a zoological park or a movie theater. Similarly, without a Spark session, we cannot actually access the features of Spark or even execute any piece of code. If we do not have a Spark session created, the code will not start executing. It will just throw some error message saying that the Spark context does not exist. So moving on, uh, if we go to Databricks platform and try to write a Spark application code, we need not explicitly create a Spark session variable, because if you create a Databricks notebook and attach a compute resource to your notebook, it by default comes with a Spark session in a variable called Spark. So we will try to see that in the next session. But for now, what you can understand is the syntax that we have just seen need to be written when we are writing our Spark application in our local computer or in our own Spark installation. But if you are using Spark in Databricks, we need not create the Spark session because it comes by default. So that's it for this session. I'll come back with one more new session very soon, and I'll try to start explaining about how to create Spark session in Google Colab and Databricks Notebook, and also we'll try to discuss some of the basic concepts of data frames and get started with coding samples, and we'll go with a real-time project after that session. Thank you guys. Have a good rest of your day. Thank you.